Welcome back, everybody. In this video, we'll start chapter 1 by looking at section 1.1. Whenever you start a new chapter, it's a good idea to look ahead and see what it is you're getting into. So we're going to give a quick rundown of what's in each of the sections. Chapter 1 overall is about functions, which we'll find out what they are in this section, but basically they're a rule that relates one quantity to another. Of course, there's more to it than that, but that's the basic part. One of the key features of functions are their domain and range. That's covered in section 1.2. Roughly, the domain is the input to a function and range is its output. So there's that. Section 1.3 is about rates of change, which has a lot to do with slope, but we'll talk about it when we get there, and behavior of graphs. So 1.3 has more to do with the graphs or the pictures of a function. 1.4 is about composition of functions. And if you think about the word composition, it sounds like you're putting together something, like a musical composition is a putting together of basically a creation of a piece of music by putting things together. Transformation of functions, section 1.5, that's about how we can create new functions from old functions by transforming them in some way. 1.6 is about absolute value functions, which is going to be a specific kind of function. 1.7 is about inverse functions, which are basically functions that undo the action of some function that we're given. But in this video, we'll just be working on section 1.1, which introduces the idea of a function. Okay, so in section 1.1, it's about functions and function notation. So the first thing to do is to define a function. A function is a relation or rule in which each input value is associated to or leads exactly to one output value. We say the output is a function of the input. The input values make up a set of numbers or set of things called the domain, and the outputs make up a set of things called the range. The way we might write this, functions often have a letter name. In math, they're often with F's, G's, and H's. So we might write here, as we've done here, F and a colon, and then an A, and then an arrow, and then a B. This says F is a function that takes elements from a set A, that would be the domain, and gives back elements of a set B, which is the range. So the set A is the domain and the set B is the range. Each domain element or domain value corresponds to exactly one range value. Typically, we use functions when we're interested in how one quantity depends on or varies with another quantity. For example, your pay at your job can depend on how many hours you work. In general, the more hours you work, the more pay you make. Of course, there may be complicating issues like tips and commissions and things like that, but basically, how many hours you work influences how much pay you make. The temperature on the sidewalk outside is dependent on what time of day it is. The length of your arm would probably be something of a good predictor of what your overall height is. Okay, so the two quantities are related to each other, and they should be related to each other in a predictable way. Okay, so taking a look at these three, or these first two relations are written out as sets of ordered pairs. We want to see if each input value corresponds to exactly one output value. Here, the input of 2 corresponds to an output of 5. The input of 1 corresponds to an output of 6, and an input of 3 corresponds to an output of 1. The input domain, or often called the X value, is always on the left, and the output Y or range value is always on the right. So we could say when X is 2, Y is 5. When X is 1, Y is 6. When X is 3, Y is 1. So moving on to the second one, when X is 2, Y is 5. When X is 3, Y is 9. When X is 2, Y is 6. In these two examples, there's a big difference between the two. In the first case, for any X value you pick out, I can tell you what the corresponding Y value would be. So if you say, well, when X is 1, what's Y? Okay, well, it has to be 6. And there's no doubt or ambiguity about that, right? That's not true in the second example. In the second example, if I told you, okay, when X is 2, what's Y? Okay, well, is it this 5 or is it this 6? That's a problem. So we want for a function to have the property that given an x value, the y value is uniquely determined. So this is an example where y is not a function of x. Whereas in the first example, y is a function of x. Because in the first case, given an x value, the y is uniquely determined. Okay, in the next set, the functions are given, or the relations are given in the form of a table. So we want to just decide, is y a function of x? Okay, in the first column, 2, 8, 1, 0, 5, 7, and 3, 2, given an x, would you know which y went with it? Suppose I said x is 5, what's y? You'd say, okay, well, it's 7. Are you sure? Yes, of course. There's the only 5 here, and it's right across from 7, so it's got to be 7, right? And you could do that with any of these numbers without any doubt, right? And so that makes it so y is a function of x. Okay, in the next one, 5, 1, 0, 3, 6, 8, 2, 3. On this one, given a value of x, is y uniquely determined. So if you pick out an x, let's say 0. When x is 0, y is 3. Are you sure? Yes. There's 0 right across from it's 3. When x is 0, y is 3. When x is 6, y is 8. When x is 2, y is 3. On this one, you might be tempted to say this one's not a function because the x value of 3 occurs twice. But if you look carefully at the definition, each input value leads to exactly one output value. It doesn't say anything about the y's not repeating. For y's to repeat, that's okay. So this one, y is a function of x. Okay, often we use variables other than x and y, especially if we're doing applied problems or story problems or something. So we should get accustomed to using other letters. Here we have variables p and g. So if I give you a value of p, would you know the value of g? Well, you can see right away that when p is 19, there are two different values of g. So here g is not a function of p. Okay, moving on. W and R. If you pick out a W, am I going to know R? Yep. No matter what value of W pick, the R is uniquely determined. So we could say R is a function of W. On the other hand, W is not a function of R. That can be a little bit confusing. We'll talk in a minute about how to make that less confusing, which is a function of which. Before we go on, though, I wanted to talk a little bit about why is it that it matters if it's unique or not. That is, why is in the first one here, why is that one better than, in a way, this one? Okay, it's because of the predictability. If you think about it, a lot of the applications in which we look at one quantity related to another, we would expect to have that sense of predictability. If we told you your arm length, we should be able to predict one value for your height from that. Assuming you don't work on tips or commission or something, if you just work on an hourly pay, if you went to work for one day and worked for 5 hours and made $70, you would expect the next day to go to work for 5 hours and still make $70. Given a specific input, you expect to have a certain output. If you go to your microwave oven and type 30 and press start, you expect it to cook for 30 seconds, no more, no less. You'd think your microwave would be broken if you went and pushed 30 seconds and it stopped after 20 sometimes, and 30 seconds start. Next time it cooks for a minute, right? For a certain input, you expect a certain output without any fluctuation. Okay, the amount of medicine that you give your kid when they're sick depends on their weight if they're really young. Okay, how much does the kid weigh? This is the amount of medicine you give. Okay, you wouldn't say, okay, well, I'll give 10, 15 milliliters, something like that. No, this is how much they weigh. This is how much medicine you give. To make a long story short, the predictability is important. For a single input, we have to have a single output. That is a necessary feature of a function. Okay. Another way you might see functions described is through these arrow diagrams or mapping diagrams. So let me show you those. So in the first case, on the left side, we have the values for x. They're 2, 1, and 3. The values for y, 5, 0, and 6. If you look here, if you start with a value for x, when x is 2, what is the corresponding y? Well, if you see, there's 2 arrows that lead away from 2. One goes to 6 and one goes to 5. So if I told you, well, when x is 2, what's y? You'd say, well, I don't know. It could be 5, could be 6. And we don't like that, right? So this one, y is not a function of x. Okay, it's the 2. That's the problem. Okay, taking a look at this next one. When x is 5, y is 3. When x is 8, y is 6. When x is 9, y is 6. Each x value is associated with only one y value. So here y is a function of x. Okay, no x's are repeated, which is important. People find that confusing though. So one way to kind of keep this straight, especially if other variable names are used, is to think in terms of what variable you're given and which variable you're predicting based on that variable. So if you want to say y is a function of x, whatever the variable is that is after the of, basically, the object of the preposition if you're a language person, whichever one comes after the of would be the variable that you are given, okay? And the other one is the variable you're trying to predict from that, okay? So the given value would be the x, function of x. The predicted value would be y. That is the value that we're predicting based on a value for x. So whichever one comes after the of, more or less, is the one that you were given. That's the one that can't repeat. Otherwise, you lose the predictability. Okay, some more kind of conceptual examples. Somewhere in COD's computer, there's files all about you, your transcript, your address, your financial aid information, everything else is in there. There's some relationship between your student ID number, like you type into WebAdvisor, and what your name is. Do you think that your name is a function of student ID? Given your student ID number, do we know your name? If you go to admissions and records and say, okay, well, here's my student ID number, they're going to type it in and they know what your name is. Okay, so given a student ID number, your name is going to be knowable or predictable using that. So I would say yes. Okay. Is student ID number a function of name? Well, no, right? If you go into admissions and records and say, hi, my name is Dan, are they going to know, okay, what my student ID number is? No, not necessarily, right? Because there could be multiple people named Dan at the school, right? So given the name, that doesn't uniquely determine what the student ID number is. So no. Okay. Does the relation y equals x squared plus 1 describe y as a function of x? Here we have a relation given by a formula. If I give you a value of x and you plug it in there, will you get only one possible value for y? Let's try one. Let's say x is 6. 6 squared is 36, plus 1 is 37. Man, it can't really be anything else, right? Given a value for x, we could calculate a value for y, and there'd only be one. So we'd say yes. Okay, if you remember what the graph of that looks like, which hopefully you do, but if not, it's okay, we'll get back to it later. That's a parabola that opens upward, that has its vertex at the point 0, 1. And later on today, we'll talk about something called the vertical line test, which you can use to help figure out whether a graph is a graph of a function or not. Okay, one involving absolute value. Does the absolute value of y equal x plus 1 describe y as a function of x? Well, again, we'll pick out a value for x and see if we get a unique y. Let's try x is equal to 4. When x is 4, x plus 1 will be 5, right? If x is 4, x plus 1 is 5. So the absolute value of y would be 5. Is there only one y that fits that description? No, there are two, right? Y could be 5 or y could be negative 5, right? So if we were to write out the table for this, we could have an x of 4. You would have a y value of 5 and a y value of negative 5. In other words, the x repeats. So no, y is not a function of x. Okay. We have special notation for working with functions, so that's what's next. By the way, I did want to mention that traditionally the x is called the independent variable, y is the dependent variable. And you could think of it like this, that if you think about someone who's independent, they kind of go their own way, do their own thing, right? When you're old enough, you become, an independent person from your parents and so forth, right? If you were a dependent or if you have dependents, they depend on you, right? And so in a similar way, the y depends on the x. Okay, so that's a way to keep them straight. All right, so just want to put that out there. So now taking a look at the table on the left, when x is 1, what's y? Well, if you're looking at the table on the left, it's a 0. If you're looking at the table on the right, it's a 4. Both of those are functions, though. I probably should have just been more specific about what table to look in. So let's try that again. Using the table on the right, when x is 5, what's y? When x is 5, y is 3, using the table on the right. So a kind of compact way of saying that is just to give the functions names. Traditionally, we'll use letters like f for function, and then letters that come right after that, f's, g's, and h's, right? So let me call this one f and this one g. When we're working on a problem that has like a story to it, we might use a different letter. We might have a cost function and call it C, or a W function and call it, or a width function and call it W, and situations like that. But when there's no story, usually we just use F's, G's, and H's. Okay, so let's try this again. Using the F function, when x is 2, y is 3. Okay, that's really wordy. We can write that in a simpler way by writing f, parenthesis, and then the input or domain value, which is 2, and then that's equal to 3. That's said out loud as f of 2 equals 3, or f of 2 is 3. A couple of other examples using the same notation. G of 2 is equal to 1. That says we're using the other function. G of 6 is equal to 9. F of 5 is equal to 9. It's important to note when you're doing this, we're not doing a multiplication. This is an example of a situation in math where we're using a similar notation to mean two different things. So elsewhere in your math life, if I asked you, okay, 5 times x plus 2, I'm sure all of you could say, well, that's 5x plus 10, right? Because you multiply the 5 times each thing inside. So here, shown in green, when you have 5 up against a parenthesis like that, it means multiply. Here, we're using a similar setup. We have a symbol up against a left parenthesis. That doesn't mean we're multiplying. That means we're applying a function, and we're giving it an input value, and we want to know a certain output value. We're definitely not multiplying. For that reason, we basically will not use F's, G's, and H's to stand for regular numbers anymore. From this point forward, you can typically think of them just as representing functions. Okay, let's try evaluating some functions. What it means to evaluate a function is to calculate the value, calculate the output value. So let's try this. F of 4 for this function. F of 4, we're going to replace the x value with the given number. So that will be 4 squared minus 3 times 4. That's going to be 16 minus 12, or 4. So on that one, it's interesting. When the input's 4, the output is also 4. You'll notice on this that when I put the 4 in place of the x, I didn't just write, I had to put a dot in there to mean multiplication, right? If I wrote 4 squared minus 3 times 4, y'all are going to think that's 34, right? And it's not, it's 3 times 4. So when you're replacing the letter by its value, you have to use some other punctuation, like parentheses or a dot for times or something to illustrate that. Okay, here, f of negative 2, that will be negative 2 squared minus 3 times negative 2. So we'll have 4 minus 3 times negative 2 is negative 6. 4 plus 6 is going to be 10. Last one, 0 is always a treat. 0 squared minus 3 times 0, that will be 0 minus 0, which is 0. Okay, just a couple more of these. If f of x is 3x squared minus x plus 1, we want to find f of 2, f of negative 4, and f of 0. At this point, you might want to pause the video and try this on your own, and then we can compare answers. Okay, so let's see how this looks. So we'll have 3 times 2 squared minus 3 plus 1. That's 3 times 4 minus 3 plus 1. And I'm getting 10. For negative 4, that's 48 plus 4 plus 1, looks like 53. And last one, 0, always a treat. Looks like that's just going to be 1. Okay, so evaluating functions. Notice in each case, of course, for any given input, we're going to have exactly one output. All right, so let's try one more. In this one, it's going to be kind of interesting because we're evaluating our function using two kind of expressions involving a and h. It's going to turn out that this particular structure is something that we'll need to refer to later on. So we're kind of having a first look at it here. So f of a plus h minus f of a. First, I'm going to go through the function f and replace it. Everywhere I see an x, we'll get a plus h. So we'll have a plus h squared minus a plus h minus 6. Okay, now you can take a little break. Minus f of a. And notice that we're subtracting all those terms. So I put all of them in brackets to ensure that all three terms get subtracted. A common mistake is to leave off those brackets, in which case we'd only be subtracting a squared, and then the signs on the other two terms would be incorrect. Okay, so now we're going to multiply out the a plus h squared. So that is a perfect square trinomial. So if you like, you can use FOIL or some other method to multiply that out. If you need help with that, if you don't remember how that goes, how did I do that multiplication, then let me know, or get help from a tutor or a classmate or something. Okay, so I multiplied that out. Let me double check and make sure it's okay. It's always a good idea to go back. A squared, 2 AH's, and an h squared, I distributed a negative, minus a minus h. The minus 6 is just a copy, and then in the last three terms, we distributed a negative, minus a squared plus a plus 6. Okay, let me go through and combine like terms now. A squared, 2AH, and, well, let me go back up. I can see that there's 2 of those a squareds, right? So a squared and this minus a squared are going to add up to 0. So that's nice. And that happens again right here. This minus a and plus a also add up to 0. So let me copy out what else I have. Looks like the minus 6 and plus 6. So those two will add up to 0. So it looks like 2ah plus h squared minus nh. And that's the end of that. So before we move along, I do want to point out these lines underneath. I'm doing that just so that I can, for one thing, indicate what terms match up with which terms, and also to make sure that I didn't forget anything. Everything that I have should be crossed off or copied in some way. You may have had other instructors who will draw lines through stuff like that. Generally, I don't do that because it makes it, I think, harder to read, and it can be a little, take more time to maybe recopy the problem if we have to do it again. Okay, so I usually put lines underneath if you're wondering what that's for. All right, so we haven't quite finished section 1.1 yet, but we want to stop the video here so it doesn't end up too long, and we'll pick it up in the rest of section 1.1 in our next video. In the meantime, if you have any questions, let me know.